So we're gonna finish up chapter 11 here, and the topic we're gonna start with is something called Pascal's triangle. And so what we have here is a pattern, and then so I'm gonna start writing it. And so I'm gonna try to draw something here that's kind of a triangle. So my first, at the top of it is a 1. The next row is 1, 1. The next row is 1, 2, 1. The next row is 1, 3, 3, 1. The next 1, 4, 6, 4, 1. And hopefully you're starting to notice maybe what the pattern would be. So there's this, so maybe you're guessing, so 1, 5, 10, 10, 5, 1 would be the next row. And so if you haven't seen it yet, really what you have, if you look and you add the two numbers above, so I've kind of drawn it here as a triangle. So I'm looking at, so in row, well, in this row 1, 3, 3, 1, I'll talk about what row I want to call it here in a minute. But if I add together 1 and 3, I get 4. If I add together 3 and 3, I get 6. If I add together 1 and 3, I get 4. And there's 1s always on the outside. So if I'm looking at this last row, 1, 5, 10, 10, 5, 1, so 1 on the outside, add together 1 and 5, 6, add together 5 and 10, 15, 20, 15, 6, 1. And that pattern would continue forever, right? We could just continue to build more and more rows of Pascal's triangle here. So there's an interesting connection to distributing as it relates to this. There's something here that we're going to talk about that's called the binomial theorem. Okay, the binomial theorem. Now, it might seem strange, but I'm going to call this first row the 0th row. That's row 0. Then the 1, 1, I'm going to call that the first row. The 1, 2, 1 is the second row. The 1, 3, 3, 1 is the third. The 1, 4, 6, 4, 1 is 4. 1, 5, 10, 10, 5, 1 is the fifth row. And so notice that there is another pattern, that the second number in that row, so if I highlight all of those, that would be in the 0th row, there's not a second number. In the first row, it's a 1 is the second number. In the second row, 2. In the third row, 3. And so the second number always appears to be the row number if I define it that way. But notice also that the next to last number would be the same. This Pascal's triangle definitely has symmetry going down the middle. So if I draw a line down the middle, that's 1, 2, 6, 20. Like thinking about the 10s are split on each side, right? So in row 5. But there's lots of symmetry and patterns here, that the left side has to be a mirror image of the right side. And so here's the big connection. Here's the big takeaway of something that we've already done before. If I would ask you to expand, multiply out x plus y to the quantity to the first power, that's not a lot of work to do. We would just write x plus y. And if I was being super meticulous or redundant or unnecessarily writing too much, I might say 1x plus 1y. And so notice that those coefficients, 1 and 1, are matching the coefficients in the first row first, because the exponent here is 1. So let's keep going. If I would say x plus y quantity squared, we've multiplied that out lots and lots and lots. And I hope you said x squared. Don't forget the middle terms. Don't say plus y squared. That's leaving 1 out. But there is this 2xy. So if you look at these coefficients, the coefficients are 1, 2, 1. which is the second row, the way I'm defining it there. Why the second row? Because the exponent here is 2. So really, there's a tremendous shortcut to this thought, because if x plus y, if this continues, and it does, if I'd ask you to multiply out x plus y to the third, that could be a little bit annoying, right? We would have to do FOIL, distribute, get that answer, and then distribute again with all those pieces. There's a lot of steps in there. But we would know right now that that answer must be connected to 1331. So I actually know right now that this answer is 1 something plus 3 something plus 3 something plus 1 something. I'll just leave some blanks in there. So then the question is, well, what are the somethings? Now let's think back to when I multiplied out here just x plus y squared. Do you notice that the powers of x, as I read these terms across, are going down? I see an x squared, I see an x to the first, I don't see any x's. I could say x to the 0. X to the 0 is really 1, which is why it wouldn't affect the answer. But the powers of x are going down. Also, the powers of y. So this first term, this 1x squared, I could have said 1x squared y to the 0. And that doesn't change anything because y to the 0 is 1. The next term has a y to the first, and the last term has a y squared. That actually has to always be true, that the powers of x have to go down, and the powers of y have to go up. Now, it's actually even a little bit more than that. That if I would think about what the exponents have to add to, they're always going to have to add to whatever the exponent was of the thing I'm expanding. I'm going to say a little bit more about that here in a minute, but to expand this x plus y quantity cubed, then we would say 1, it's got to be an x cubed, y to the 0, but I don't need to write that because that's a 1. The powers of x will go down, so the next one would be x squared, but then that's got to be a y to the first, plus 3 x to the first, so I don't need to put the 1 there, but just to emphasize it, y squared plus 1 y cubed. And that is the expansion of x plus y cubed. Now, remember, really what you're doing is the quantity x plus y times the quantity x plus y times the quantity of x plus y. And we think about multiplying, think about distributing, thinking about, that FOIL acronym when it's these two terms and these two terms, and it's the first and the outer and so on. Here's the end result. Like, this x will never multiply that y. In fact, really what's going to happen is that this x needs to multiply 1 of either that x or y, and then 1 of either that x or y. And then we do all the possibilities. So one possibility is take this x times this x times this x, and that's an x cubed. There's no other way to get an x cubed, right? I have to pick those 3 x's. There's no other choice I could make to get an x cubed, which means there's only one way to get an x cubed. If I think about the next term here, this 3x squared y, how I like to think about it is that there's 3 ways to get an x squared times a y. Okay, so let's see if we can count them. So I could pick this first x in this first x plus y. I could pick the second x, and then I could pick the y in this last term, and that's one of them. Okay, so let's think of other possibilities. So I'm just gonna rewrite x plus y, x plus y, x plus y. So another choice I could have made is I could have chosen the y in the second one. and chose the x in the first one and the x in the last one. That's very different than the first one, so I would count that. There's another, I don't know what that is. So this is a 1x squared y, this is another x squared y, and then finally there's one more, and hopefully I don't need to write it out, but it would be choosing this y and then the other two x's. And then there's no other way to do it, so then there's 3 of those. And then so this is saying there's 3 ways to get 1x and 2 y's. Now, what that partly is explaining is the symmetry in Pascal's triangle. So if I wrote out these 3 terms, x plus y, x plus y, x plus y, I'm going to multiply them all together. And I want to pick 2 x's and 1 y, and we said that there's 3 ways to do that. Well, isn't that the same as picking 1 x and 2 y's? It really has to be, because when I'm thinking about choosing an x or a y, I only have those 2 choices. So how many ways can I choose 1x? Well, it'd be this x, and then this y and this y, or this x and this y and this y, or then the third x and then the first y and the second y. That's kind of just like going back to my first example and choosing y. So that actually explains why in Pascal's triangle we see the left and the right side being the same, that they have to be the same. And we're going to talk a little bit more about something called a combination here and how it's related. Okay, so let's see if we can extend this a little bit. Okay, so I'm not going to go too far on us here, but what if I would just say x plus, let's say 3y squared. Okay, now I know that we could write this out, so the quantity x plus 3y, quantity squared, we could say x plus 3y times x plus 3y, and distribute x squared. We get a plus 3xy, we get another plus 3xy, we get a 9y squared. Like terms in the middle, final answer x squared plus 6xy plus 9y squared. What I want to do is see if Pascal's triangle will help give an answer for a question like this, which it will. So let's talk about how. And so what I want to do is kind of lump together that 3y. I'm going to highlight it here in yellow. So I just want to think about that as yellow blob, red squiggle. So x plus yellow blob squared. And so really what Pascal's triangle then would say, like, so it doesn't matter, the x is really insignificant, it's just a label. Y is insignificant as a label. So what if I actually scribble out the x too? So I have here black squiggle plus yellow squiggle quantity squared. So what Pascal's triangle would say is we would have one black squiggle squared plus 2 black squiggle, yellow squiggle, both to the first power, plus 1 yellow squiggle squared. Right? There's our 1, 2, 1 pattern going back here to Pascal's triangle. Okay. So now we just need to fill in like what's black squiggle and yellow squiggle. So black squiggle is x, so 1x squared plus 2x to the first plus yellow squiggle, which is just 3y, plus 1 yellow squiggle squared. Now here, careful, we want to square everything that yellow is. Yellow is 3y, so I square all of 3y. Final answer here is actually the same thing we wrote down. So I get a plus 6xy and a plus 9y squared, which is the same thing we just said. Now you might go, well, that seems harder. Why would I do that? Well, what would you do, though, if I said this? What is, let's use different letters. So what if I would say a minus 5b quantity to the fifth. Now, in this one, I would need then this fifth row. So I'll go back here, and we're going to talk about how we don't have to write these all out here soon, but the fifth row is 1, 5, 10, 10, 5, 1. I don't think I'm going to do all of this, but I just want to give a taste for it. So the fifth row, 1, 5, 10, 10, 5, 1. And so our first term, so if I think about, let's squiggle it out. So that's a blue squiggle, minus, now it says minus, and so we'll probably need to be a little cautious on how we treat it. So let me actually back up one step. I might suggest we rewrite this as A plus the quantity negative 5b, and that whole thing, A plus that negative 5b, all to the fifth. Now, here's why. Like that minus, what should be happening is it's going to make your signs alternate, and you know this. At least you've seen it. Like if I would say x minus y squared, then I get an x squared, a minus 2xy, and a plus y squared. It's a positive, negative, positive pattern. And so we're just going to make it a plus to make it kind of fit better, and we'll see why it has to then alternate. So let me go back to my pattern now. So I'm going to blue squiggle. I'm going to scribble out A. So green squiggle, I'm going to scribble out negative 5b. So what I'm trying to do is make it look just like x plus y to the fifth. So here we should say something like 1 blue squiggle to the fifth power. So I'm going to jump and just say a to the fifth, plus 5 blue squiggle, so everything blue squiggle is just a. That's going to be now to the fourth power. Green squiggle, everything that it is, which includes the negative and the 5 and the b, to the first power. Again, these powers here have to add to equal the power that you're starting with. So 4 plus 1 is 5. And then this would continue. So 1, 5, 10, a cubed times the quantity negative 5b, that whole thing squared, plus dot, dot, dot. So you can finish this one on your own, but obviously there's work you could do because the 5 and the minus 5 in that second term is really a minus 25. In this third term, be sure you square the negative and the 5 and the b. So this second portion here should be 25b squared. So we'd have 10a cubed times 25b squared, and then so that's 250 a cubed b squared, and that's a plus. This second term would have been a minus 25 a to the fourth b, and the first term was 1a to the fifth. And so you can see here also the signs alternate. Well, positive, negative 25, positive 250. Okay. Now that probably leads though to a question of what would happen if I ask for something a lot further ahead, a lot bigger value. And so what I want to do is try to see if I can get just one number in Pascal's triangle without producing the whole thing. Okay, so actually let me just rewrite it here. So 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, and so on. And there's something that we're going to use. It's something called a combination. I'll get my calculator up in a second, so I'll pause the video, but the notation is going to look something like this. It's a parenthesis, and then inside of it we're going to write a 3 and a 2 vertically, kind of like we were doing a matrix. There's no division sign there, don't do that, but it's kind of like this one, just a set of parentheses, and in it we see this vertical 3, 2. Now, what that's really saying is this. It would be, so here's another way it's written. 3 kind of as a subscript, and then we would have this C, like capital C, and then 2 as a subscript. Your calculators, some of your calculators would think of it this way, 3, and then it would say NCR 2. And all of these are notations that say 3, choose 2. 3, choose 2. Now, some of these calculations are super simple, like that. This is one that we could do without a calculator. And so I want to talk about how you get an answer to a combination. Like really what this is it's a notation telling you to do something, this 3/2. And what it's really saying is this. It's saying 3 factorial over 2 factorial, and it's also divided by 3 minus 2 factorial. Okay, so you're going to subtract the numbers, and that becomes a second thing you're dividing by. And so this becomes 3 factorial over 2 factorial and 1 factorial. So it's divided by both of those. Now, factorial. What is a factorial? Well, you probably have seen this before, but like if I would say 6 factorial, it would say, really what I'm saying is 6 times 5 times 4 times 3 times 2 times 1, and stop. If I say 2 factorial, I would say 2 times 1, stop. If I say 1 factorial, it's 1. And here's something that is important, but 0 factorial is 1. You might want that to be 0, but it actually has to be 1. It doesn't make sense, and we'll see why in the choosing here in just a minute. It has to be 1, okay? This doesn't make sense, -2 factorial, because that would say -2 times -1 times, -2 times -3 times -4 times, and you're supposed to stop at 1, but you never get there. Now, before you think I'm wrong, if you type in your calculator -2 factorial, you might go, wait, my calculator said that answer is -2. Well, it's not, because of really order of operations. Like when you type -2 factorial, factorials are higher in the, if you think of those order of operations. So it happens first. So that would say you're telling your calculator, find 2 factorial, and now take the opposite of that, which is not what we're talking about here. So so in this problem, 3 choose 2 would be 3 times 2 times 1 over 2 times 1, also over 1. Now, a lot of times with factorials, we can get things to cancel out, and that's why I don't necessarily need a calculator here, but the answer is 3. Also, if I would ask to do this calculation then, so parenthesis, 3 over 1, so I'm saying 3 choose 1, that would say 3 factorial, so it's this number on top, 3 factorial, it's the number on bottom, 1 factorial, and then it's the difference between the two numbers, which is 3 minus 1, which is 2 factorial. And notice that that's really the same calculation. Now, go back to what I said, that we're saying 3 choose 2. And these two calculations are both producing the number 3. Well, this is exactly what I was saying a minute ago. Like if we would say x plus y cubed, and that's x plus y and x plus y and x plus y. If I'm looking for the x squared y to the first term, aren't I taking those three terms and choosing two of them to give me an x and then choosing one of them to give me a y? Right? Isn't that what we were saying? I'm going to pick that x, and then I'm going to choose that y. Or I could have chosen this x and this y and this x. Or I could have chosen this y and then this x and this x, right? Like I had three different ways that that could have happened. And that's actually what like the first calculation here is doing. I'm choosing two. But the second calculation we did is a lot like it. Why? Because choosing one out of three things is the same as choosing two out of three things. Here's an analogy. Like if I would have three people, okay? So we have John, and we have Jill, and we have Jack. And I have these three people here, and I'm saying I want to choose two of them to do something. Well, I could choose John and Jack. I could choose Jill and John. Or I could choose Jill and Jack. Right? There's no other pair I could make. So how many ways could I choose two people to do something out of a group of three? Well, there's three ways. There's three different pairs of people. But do you notice that has to be the same as choosing one? Because every time that I choose two, so if I look at the two, John and Jack, well, didn't I really choose Jill to not participate in that group? Or if I look at the blue group, Jill and John, by choosing Jill and John, didn't I also choose not Jack? Or by choosing Jill and Jack, didn't I not choose John? So not choosing John is the same as choosing Jill and Jack, which is why we have this symmetry again, that choosing 3 out of 2 is the same as choosing 3, I'm sorry, I said that wrong. Choosing 2 out of 3 is the same thing as choosing 1 out of 3. Which takes us back to Pascal's triangle and why we see this symmetry, this 1, 3, 3, 1, we see the symmetry of those choices. Now, if I extend this, so let's go 1, 4, 6, 4, 1. 1, 5, 10, 10, 5, 1. So let's think about how to get just the second 10 in that list, 1, 5, 10, 10, 1. So we are multiplying out an x plus y to the fifth. Okay, so that's what we're multiplying out to get something like that. So if I'm looking for that second 10, so that calculation should have been, so think about the powers of x. Powers of x here would be going down. So that's an x squared term. The last one is x to the 0. And the powers of y should be going up. 3, 4, 5. So the term we're talking about there is x squared y cubed. So instead of thinking of adding the 4 and the 6 from the row above it, we could do this calculation. 5, so 5 parentheses, and then put that vertically over 2. Now, I'm kind of thinking of the number underneath here as representing the x's just because they come first. But remember, because of the symmetry, it would be the same as this 5 over 3. Like they've got to be the same. So if I would think about this second 10, I could then say, okay, that is 5 factorial over 2 factorial over the difference of those numbers factorial. And so that would be 5 times 4 times 3 times 2 times 1 over 2 times 1 times 3 times 2 times 1. And a lot of things cancel out. 3, 2, 1, 3, 2, 1. They cancel out. The 1 doesn't matter. This is 20 over 2, which is 10, which is our answer. Okay, so if you're getting this, then that means you could do this. Suppose I want to multiply out x plus y to the 20, let's say 18th power, okay? Now, what if I don't want every row? I don't want that tedious of writing that all out, okay? So I'm not going to do that. But what if I actually only am interested in the coefficient of the term that would be x to the, let's say, 7th power, y to a power I'm not going to tell you. And I want to know what that coefficient is without taking all of the investment of writing out all these rows of Pascal's triangle. Okay, so first thing is, what is the exponent of y? Well, again, I would be writing out x plus y, x plus y, x plus y, x plus y 18 times. Out of those 18, I'm going to choose 7 of them to give me an x. Well, if it doesn't give me an x, it must give me a y. So the exponent here of y should be 18 minus 7, so 11. Again, those will always add. And then so this coefficient should be 18 choose 7. Or 18 choose 11. It doesn't matter, because if I have a group of 18, if I think about a class of 18 and I say I'm going to pick 7 of you to go outside and do something, well, didn't I also pick 11 of you to stay in the class? Like, I could have said it differently. I could have said I'm going to choose 11 of you to stay in the class and then 7 of you to go outside. So choosing 7 people out of 11 would be the same as choosing 11 out of the choosing 7 people out of 18 is the same as choosing 11 out of 18. And so here, our coefficient should be 18 times 17 times 16, 15, 14, 13. And this continues down. And this is when we're going to want our calculator to do this a little bit simpler. But I want you to see something here that I'm going to, instead of write 7 times 6 times 5 times 4 times 3 times 2, etc. So I just have 18 times 17, 16, 14, da 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 da. And I'm just going to say the last one here is 7 factorial over 7 factorial. And that's also, I need an 11 factorial. So I actually could have, let me actually do this differently. It doesn't really matter. There's a lot of things here that could cancel. I could cancel these 7 factorials right now, because 7 factorials is 7, 6, 5, 4, 3, etc., all multiplied together. Or I could cancel this 11 factorial with 11 and then all the way down. And then if I wanted to, I could type this into my calculator, 18 times 17 times 16, 15, 14, 13, 12. Everything else is gone. And then this 11 is gone in the denominator, so all I'm left with is the 7 times 6 times 5 times 4 times 3 times 2 times 1. And I could try to clean that up a little bit or get an answer, but let me get my virtual calculator here up. Okay, so what we'll do is, let's suppose I just want to type that into my calculator, and where you want to go is into this math menu, and then you can go over to probability. And you can see here NPR, NCR, and even factorial. And so we're choosing combination here. So we're going to, well, if I choose NCR now, so the number has to come first here. So I need to then say 18 NCR. So 18 choose 7. And my calculator will spit out the answer for me of 31,824. So just to kind of test what I'm saying, if I'd go back into this math menu, and I would choose, actually let's do it this way. If I just go and choose my answer, this calculator doesn't let me. So let's say 18 choose 11. And so it better tell us the same answer, and it does. Okay, so that's what I'm saying, choosing 7, choosing 11, you're making the same choices. Now, just to see that how we're doing it here would also work, so in your calculator, you can, like, if you wanted to, you could type this all in and show that it works. You could even type the factorials in directly if you wanted to also show it works, and they're in this math menu probability as well. Okay, so the last question, so here's the challenge question. Here is as hard as it gets when we think about binomial theorem and putting these pieces then together. Okay, so if I would say 2x plus y, and that quantity to the 15th power. And suppose I'm looking for a coefficient, just one coefficient here. I'm looking for the coefficient of the x to the, let's say, 9th term. Y I'm not going to tell you. Okay. So there's two things that are happening here. And so this y value is the first thing, which is an easy thing, which look here, and you should be able to say that the answer is 6. That means that when I'm thinking about my combination, that I'm should be having something like 9 15 choose 9. Okay, again, 15 choose 6 should have been the same answer. So, but again, now that I have my calculator, I could just type that in, but that'll be wrong. That's not enough. There's another part to this that we need to remember from the other part of the lesson. Okay, and what we have there is that, remember, I had scribbled out this like 2x, and I thought of, when I wrote this, I was saying something like, that whole thing is being raised to the 9th power. So really what you have here then is 2x to the 9th, y to the 6th. So the quantity 2x is being raised to the 9th, because really this 2x, they're linked together, they're tied together. So if I want 9 x's, then I also get 9 2's multiplied together. Okay, and then, but we also get out in front here the coefficient from Pascal's triangle. So this ends up being 15 choose 9. So 15 factorial over 9 factorial, 6 factorial. We're going to get that answer from our calculator, but then we're also going to get a 2 to the 9th. And that will be together, those two pieces are the coefficient of x to the 9th, y to the 6th. So there's a little bit about combinations and also binomial theorem, and hopefully that's helpful to get us well on our way for 11.5. So we'll have a Zoom session soon on this, but definitely work on this, see what you can do putting this together, and I'll see you. Have a good one.